I think we lost a few bodies there. Hopefully they find their way back. We're going to talk about designing with hydronic heat pumps. Spoiler, none of my training is ever the same, including when I tell you this all again. So I got lots of pretty pictures, but I don't need said pretty pictures. So we're going to go through the training. I covered a lot of ground here. I apologize. There were some technical issues. Hopefully we don't have any now. As I alluded to at the beginning, I have an extensive background with hydronic heat pumps, hydraulics in general. Worked in the industry now for too long. And so today the goal is to give you a basic understanding of hydronic heat pumps. You're not going to leave this 1 hour presentation as an expert, but I want to sort of walk through some of the opportunities and challenges specifically about deploying hydronic heat pumps. And I want you to obviously understand that today's 1 hour session is not going to make you an expert. It's not going to replace tech support, proper technical training, and it certainly is not going to replace proper engineering. So follow manufacturer's instructions, follow local codes, et cetera, et cetera. So as we talk about sort of what the air-to-water advantage is, we need to sort of understand, why do I want an air-to-water? Well, right off the bat, an air-to-water has very distinct advantages in that it's basically an air-to-air heat pump that is typically a lot easier to work with. It's going to be moving energy more than it is generating energy. And we'll dive into what that means exactly. But in the wintertime, we're extracting heat from the air. And in the summertime, we're rejecting heat from the building out into the air. What is really interesting, though, is that air-to-water heat pumps are typically a monoblock design, which means that it's a basic water glycol connection from the outdoor unit to whatever configuration you might have as an indoor unit. It could be prepackaged. It could be something you've put together with the help of your wholesaler and a local engineer designer. But air-to-water heat pumps have some very, very distinct advantages. And most importantly is its ability to do heating, cooling, and hot water. So what we've seen historically is that people will put boilers in. They'll use those boilers for radiant floor heating. They might put an indirect on it for hot water. And then for cooling, they'll put an air source heat pump in. Well, the reality is with an air-to-water heat pump, you're actually replacing 3 appliances. You're replacing the gas boiler, you're replacing the air source heat pump, and you're also replacing your method of doing domestic hot water. So you're going to deliver comfort, and you're going to cover a lot of different applications as part of doing that. Now, we talked about this and we said that air-to-water heat pumps, and frankly, all hydronic heat pumps, they're going to move more energy than they generate. So if you were to look at an air source heat pump, whether it's air to water or air to air, they're going to have varying overall COPs that are going to be anywhere from like 1.7 to up to 4, depending on how you're using and designing it. So when you see a COP of 3, for example, what that means is for every kilowatt of energy that you are purchasing, you're going to get 3 for free, right? That's the advantage of the COP system. So if you compare that to a typical gas system, you're going to be about 320% efficient, because on paper, a condensing gas boiler is typically going to be 95, 96% efficient. So the real beauty of a hydronic heat pump is the ability for the COP to result in better comfort with reduced operating costs, with obviously a few caveats. So with the heat pump, whether it's air to air, air to water, water to water, water to air, there's a lot of different configurations. COP is king. And one of the really distinct advantages about an air-to-water system is we have a lot of control over what that COP can be. And we're going to talk about that, as well as different ways that we can do heating and cooling inside of the space. So air-to-water advantage, we talked about this before. It's one system with many roles. It does heating, cooling, and it also does hot water, which is great. The other thing that's really good about it is because it's a monoblock design, it also allows for faster installations. It's going to reduce my construction installation time. And I'm not actually talking just about the air-to-water heat pump. Obviously, with the skilled trades shortage, we want to make sure we have a really, really easy system to install. So when you've got a monoblock heat pump that just needs a water glycol connection from the outdoor to the indoor, that's pretty simple. It's a factory charge packaged unit that sits outside of the building, very, very easy to contend with. But the other thing when we talk about faster installs is when you deploy an air-to-water heat pump, depending on how you utilize that technology, you can actually dramatically increase the productivity of your builder. You can eliminate bulkheads. You can eliminate a lot of labor. So air-to-water heat pumps will be more money than other traditional heat pumps. But remember, the air-to-water heat pump does heating, cooling, domestic hot water, and it's also a future-proof technology. So when I was originally talking about air-to-water heat pumps, which goes back many years now, there was, a lot of excitement about air-to-waters and a little bit of a struggle of like, how do we use them? How do we deploy them? And when we talk about future-proofing, one of the really cool things about air-to-water heat pumps is utilities really don't realize yet, but they're starting to figure out that air-to-water heat pumps are good for the grid. They're actually better for the grid than some other heat pumps because of how we can utilize them. And specifically, it has to do with load shifting. We're going to talk through some real world research and how we can do that without getting crazy, without over engineering and making the system super complicated. The other advantage that obviously the air to water has is what I said from the beginning. Traditionally, we're doing boilers and some sort of forced air cooling. The beauty of it is with the regulatory trends driving us to get away from natural gas, it means that we can use the air to water heat pump for doing heating, cooling, and hot water. It's a fully electrified system. And when we design it right, we can have a really, really high system COP. So want to sort of talk through some of the different scenarios we can do. And we're going to go through two different scenarios on how we can heat and cool a space using a hydronic heat pump. I'm going to be using an air to water heat pump, specifically the air to water heat pump that's in my house. And apologies, this actually is my house. If you're wondering why is somebody cleaning it, that's my son. Plumbing and HVAC was taking pictures for an article, and my son was cleaning the unit. I was like, hey, this will make for a good photo for a slide. So that's my son cleaning the 5-ton air to water heat pump installed in my house. The Easter egg I'll leave with you, and you can reach out to me after the session. I have no hydronic heating in my house whatsoever. No radiant floors, no radiant ceilings, no radiant walls. I do have something from my presentation in my home, and let's see if you can figure it out. But that's what a 5-ton air-to-water heat pump looks like. When it's running, you can't even hear it running. So as we sort of get back to what we're going to do today, we're going to talk about heating, we're going to talk about cooling, and we're going to get on the gotcha of humidity. So specifically, we're going to talk about sensible latent cooling. And I want to be very, very clear that sensible and latent cooling issues are showing up everywhere. It has nothing to do with the fact that it's an air to water heat pump, but we do need to be very careful with that depending on how we cool the space. So I've chosen my home as the example. So in my particular case, I live in Guelph. So the outdoor design temperature, typically we're looking at about -4 to -8. It depends on like how bad, to what point are we doing to 1%? How are we going to look at what we're doing from a heating standpoint? So the nice part is even if we look at that design temperature to cover 99% of the year using just the heat pump with no backup heat, we can get a really high sustained COP. And again, that's every unit that we pay for. We want to get at least 3 units back for free because we're moving energy into the building, or in cooling, moving energy out of the building. And with an air to water heat pump, unlike other heat pumps, we actually can do it. And the reason for that is that we have the control over what is the temperature that we are delivering to our air handler. What is the temperature we're delivering to the slab? That's where we can do really cool things with an air to water heat pump. Doesn't change the fact that there's applications for air to air, there's applications for ground source heat pumps. Every heat pump has its place, but in a hydronic application, air to water heat pumps have a really, really key role to play. So the cooling challenge that we have is typically cooling degree days. It's about 450 cooling degree days. The worst case we'd see is somewhere around 30 degrees C, 86 degrees Fahrenheit. Although I'm pretty sure this past summer we saw some very, very hot temperatures. It's a pretty moderate, sensible cooling load. And the real temperature when it stands with us doing cooling with an air to water system, it's not really the temperature, it's the temperature and the humidity. It's the humidity gotcha. The summers are getting hotter, but they're also getting wetter, and we're seeing increased latent loads. And we cannot, with the way that loads are shrinking and shrinking, rely on cooling to take care of that latent cooling load because the equipment's not running as long. So you end up with thermal comfort issues that, again, they'll show up whether it's an air to water or an inverter-driven air to air. We just have to understand what we're dealing with and what it looks like. So in this particular case, I'm using what's in my own home as a great example to sort of illustrate what I'm doing. There's a few variables that are not in my home that we're going to talk through, but the key is that everything we're talking about right now you can do. So in my house, I have what's called an HPX5. It's a 5-ton air-to-water heat pump. It's being controlled by a Sky 35 controller. So the Sky 35 controller controls heating, cooling, domestic hot water, basically everything I need, including the buffer tank. And then the other thing that's really important beyond the buffer tank, which we're going to tie into, is that sensible latent cooling. How are we going to control sensible and latent cooling? And that's where a centralized dehumidifier, for example, a Santa Fe product or an April Air product would be a really, really good application to make sure you have a successful installation. So right off the bat, one of the things that's really important, and this came up in a recent talk that I was doing for a builder association, is that we have to understand what loads look like. And we also have to be careful that when we're designing around systems, we're designing in such a way that it does make sense and we can do it. Sort of these days of, it's 20 BTUs per square foot. If it's heating, it's 15 BTUs per square foot. If it's floor warming, you got to be really, really careful. Like if you start looking at houses that are built in the 80s, yeah, you might have 25 to 30 BTUs per square foot. But if you look at modern homes and how they're being built, especially as you start getting into near net zero, which is a very, very popular term with builders, is the loads are getting smaller and smaller. Like 7 to 12 BTUs per square foot is not unheard of. So when we see a 5-ton heat pump, which is roughly 60,000 BTUs, we usually look at that and see 60,000 BTUs and go, well, that's just nowhere big enough. I've always put in a 115,000 BTU IBC, Navien, whatever brand you put in. But we've got to understand, just as technology has evolved, so has the building envelope, so has the actual mechanical loads. Same way where sensible latent cooling loads are changing. So we want to make sure when we're designing systems, we're designing them appropriately. In the same token, this is not a conversation about, flow rates and pumping, but we also have to understand that we can deliver a lot of BTUs in an air to water application with a single small little Taco 0015 circulator. Chosen the Taco 0015 because my good friend Dave Holdorf was doing training here today as well. So a Taco 0015 can cover a really, really large home, right? At 8 gallons a minute, we can deliver a lot of BTUs out of this space. It can be upwards of the entire 6 tons can be delivered into the space just using a single circulator. So the beauty of an air to water system is we got to understand that loads are getting smaller and we can achieve a lot with a very simple baseline system. So as we look at some of the design load conditions, we talked about this earlier, but we're looking at a design heating load of roughly 33,000 BTUs, a design cooling load of roughly 21,000 BTUs, and that would peg my HPX5 at about a COP of 3.1, depending on what I'm doing from an emitter standpoint. So we're going to sort of dig into what this means and how we can achieve this. And we're going to start with a very basic heating system. So this is a heating system we would all be familiar with, right? So this is a photo that was supplied to me by a customer. And this is just your classic radiant floor heating system. So the reality is, if you were to look at the COP of an air to water heat pump, regardless of who makes the unit, and if you were to assume about 100 degrees, throughout the wintertime, 90% of the time, you can probably achieve a COP of 3.5. which means the unit is 350% efficient. Now you start getting into a baseboard application at 160 degree water. If you've got a high temperature air to water, typically an R32, R134 dual system, you could get up to those temperatures, but your COP is going to drop off dramatically. But the reality is most hydronic heating systems through the slab, we can design them around 100 degrees Fahrenheit, and we can hold on to a COP in excess of 3 very, very easily. So compared to the efficiency of a gas boiler, you're going to get higher efficiency and good comfort, and the air to water heat pump is not going to have a problem getting to those temperatures. Really, what's really cool about an air to water heat pump, and this is a graph that shows the different COPs at different temperatures, and where air to waters are really slick is that we have the opportunity to choose what we're going to do inside the space. So typically, if we were going to do a boiler, we do a radiant floor heating system. We're going to hold that slab at 84, 85 degree surface temperature. So what that means is that we can easily achieve a COP of 3 the bulk of the year. And these different temperatures that you're seeing here, these different lines, they're representing COPs at different temperatures. And I'm going to call out one in particular that I want you to look at. So if we look at -4 degrees Fahrenheit, this blue line at 95 degrees Fahrenheit means at design, so the degree design day, we could maintain a COP of 3.1. That is very, very hot, right? So if we were to compare that to like a traditional air handler at 140 degrees, we'd be way down here. Hopefully you can see my mouse okay, right? So at 140 degrees, we would have less than a COP of 2. So comparable to other heat pumps. But I want you to keep this 95 degree number in mind, because typically people see that 95 degrees and sort of goes, whoa, what's going on? I can't possibly use 95 degrees to heat the space. And the reality is we potentially can. And I'm going to walk through a scenario where we could potentially achieve that and how it has a massive impact on what we can do from a heating and efficiency standpoint in the space. So one of the things I would like to touch on that we've sort of gone through before is sort of understanding that myth of the warm floor. The objective with us designing a hydronic heat system is we're not trying to drive BTUs into the body. We're not trying to overheat you. We're trying to keep the space comfortable. And there's this sort of a misconception as we look at the heat transfer coefficient of either a floor or a wall or a ceiling that we're trying to deliver a lot of BTUs into that space. But the reality is, if you looked at a modern load at 18,000 BTUs, which seems insane, but if you look at a lot of the new houses that are being built, most of them are taking a 1.5 to 2.5 ton heat pump, and you convert that into BTUs, and you find out that the 18,000 BTUs per hour in a new building is commonplace, which means you only need 10 BTUs per square foot. It's not a lot of heat that we need to get into that space. So we need to really understand that. And the other thing I really like to point out too is that air to waters are really designed well to deliver that 100-degree water into the floor to try to heat the space. And you will occasionally run into this, and I like to always have a slide anytime I'm talking about hydronics, where sometimes people get freaked out going, hydronic heating, it can be really hard on hardwood floors and it's going to cause problems. It's just not that worth the headache. I think most people don't have this conversation anymore. They're more focused on radiant cooling, which is a concern we need to worry about. And I like to have this photo just from the standpoint of sort of showing everybody, here are the maximum subfloor temperatures we should be using, period. And the other thing I like to point out is have some pictures of cats. Who doesn't like cats? I'm deathly allergic to cats, and I still like cats. But the reality is cats sleep in the warm sunshine because the floor is hot. So if you ever have somebody say, hey, wait a minute, you can't put radiant floor heating under the hardwood like they did in my house, wrong house to do that. Just remind them that where the cat is sleeping because of the windows, it's definitely hotter than 85 degrees and there's no hydronic heating in those houses. So I like to include this nice little caveat. When we look at the air to water and sort of understand how many BTUs can I actually deliver into that space, if you look at a 110 degree average water temperature, again, just using a standard radiant wall with a 68 degree room, you can deliver over 30 BTUs per square foot into that room. It's significant. So radiant walls and radiant ceilings aren't that popular, but they are a great way to do it, especially if you're in a retrofit application. But you can deliver a lot of BTUs with a very, very low temperature that's designed perfectly for an air to water heat pump. So if you remember earlier where we said 95 degrees, if we could deliver a 95 degree average water temperature, we could maintain a COP in excess of 3, so 310% efficient at the design day. Well, here's a great example of how we can do that. If we look at a 90 degree average water temperature, we can actually deliver 17 BTUs per square foot into the room, which is significant, and we want to be aware of that. One of the other things that's really, really cool, and I've done this in my own home, is if we start to use some of the new dry panel systems that are made by manufacturers like Uponor and Rayhow and Heatlink and others, they have some really cool aluminum panel systems that can deliver a lot of BTUs. And I had a picture of one in the previous slide. So if you were to look at, for example, a ROW panel system with 110 degree average water temperature, you can get 30 BTUs per square foot. So if you remember back to what we said about how houses have lower and lower loads, we don't need 30 BTUs per square foot as long as they close the windows in the wintertime. So the reality is we have the ability to pull that water temperature back. And in my own home with the ROW panel system, I actually had sub 90 degree water that was heating the space because I didn't need 30 BTUs per square foot going into that space. So air to waters are new technology, but dry panel systems like this that you can utilize have been around a long time, and they really, really matter with an air to water heat pump. When you look at the condensing efficiency of a boiler, if it's condensing and we continue to drop that temperature, there isn't as many gains as when you put an air to water heat pump in and go, no, we actually do want to get our temperature below 120 degrees and maximize the efficiency so that even at design, we can have a really, really high COP. And it's not really complicated. It's still just a hot line and a cold line going to an outdoor unit instead of a boiler in the room. It's a water-based system. The only thing different is we need to be more conscious of the water temperature. Now, the fun part is the radiant slab cooling side of it. So radiant slab cooling makes me nervous every single day I talk about it, right? The risk in a radiant slab system is the condensation. Doing radiant cooling is not like doing cooling with an air handler or a low temperature convector. We need to be aware of the risk. And the radiant cooling is fantastic, but the challenge we got to be aware of is the humidity, right? Occasionally in the summertime, we'll leave the windows open in my house and I've got a smart thermostat in my home and it'll send me an alert and go, whoa, you've got a humidity alert. I'll take my phone, I'll log in. The relative humidity in my home will be at like 70%. It's absolutely insane. So imagine in a radiant cooling situation, well, what happens if somebody opens the windows in the middle of the summertime and we've deployed a radiant cooling solution? So I want to sort of walk through and talk through what that means. So if you're going to do a two-part solution, you need to look at it sort of as a belts and suspenders approach. You need to have a proactive and a reactive solution to What happens if I'm doing radiant cooling? Number one is, how do I make sure it's going to work if I'm using a slab? And number two, how do I overcome the human element, i.e. the unintended consequences of putting in a system, you've got everything working the way it should be, and then somebody throws a monkey wrench in, like leaves all the windows open, and you never figured, why would you cool the home and leave all the windows open? Now, I had two handouts available, but I think Francesco's probably going to tell me they were in the other presentation. So two handouts you're going to get. One is a radiant cooling design. I'm sure they'll email them to you. And the other one is just a Cleffy manual that I'm pulling some imagery from that is super helpful. Francesco?
Yeah, it was probably on the other one. So.
Okay. Yeah, so there is a couple of handouts I'm going to reference. Bug Francesco and Leah. Alternatively, hit me up on LinkedIn. I'll happily share the documents. I want to give credit to a couple of the organizations that have some great research materials. So one being Uponor, the other being Cleffy, as we sort of go through this presentation. So when we look at radiant slab cooling and the core problem, a little play on words for you there, the fundamental risk that we face is condensation, right? When we're cooling a slab, we have to be careful about the room's dew point. And the key thing you need to keep in mind, and again, it's that proactive and reactive approach, is that even if you design the perfect system, you have to be conscious of the unintended consequences, right? And we're going to walk through this very, very high level. But the reality is that you can design the perfect system, somebody leaves the windows open, perfect system comes to flaws if you don't have a backup plan. So the problem we're faced with is that when we're cooling a radiant slab, if we drop below the dew point, we're going to have condensation, we're going to have moisture damage, we'll have microbial growth, and eventually we're going to have a very, very big problem. We don't want that. It's a two-part cause, right? From a climate standpoint, summer humidity creates high latent loads. This can elevate the indoor dew point. And the other one is occupants, right? We can't control occupants. I can remember people reaching out to me on heating saying, can you come up with a control strategy that turns the heating off, because we have rental properties and they'll show up to the rental properties and for whatever reason, they'll just open the windows, even though the heat is on. Like, you have to keep the human element in mind. So as we look at it, we have to be focused on sensible and latent cooling. And we have to recognize that radiant systems are able to absorb sensible heat, which is no problem, but there's better ways to remove the latent heat, which is the energy stored in moisture. And this would be true whether you're doing air to water or air to air, right? So if we were just look at a home right now, it's not an air to water system, it's an air to air system. What happens as the air conditioning is running less and less because the loads are getting smaller and smaller is you start to have an increase in humidity. So you'll see people like Gord Cook and Robert Bean, who are building science experts, love listening to them talk. And what they're advocating for is we need to treat sensible and latent cooling as separate loads that get handled differently. It's not that complicated, but we need to deal with it. So that's true whether it's an air to water or an air to air. Really, the key things we need to keep in mind is, one, we want to keep the surface temperature above the indoor dew point temperature. And we also want to make sure that we are always in a scenario where condensation is not going to happen. So that is through proper controls, and it's also through proper mitigation. So if we look at the scenario we had, so I put a load out of 20,980 BTUs. That puts our required load at roughly 17 degrees Celsius. Well, the challenge with that is if you look at the design manual, the radiant cooling design manual that will be emailed to you guys, you'll discover that typically we're only going to be able to pull about 11 BTUs per square foot out from a radiant cooling from the standpoint of the sensible energy. And that's also assuming that we're doing it where we don't drop below the dew point. So what we're looking at is we want to make sure that we have cold enough water that will cool the space, but not so cold that it's going to cause the floor to condense. And that's where it's really, really important that we understand that if you're delivering 66-degree water into the floor to try to cool the floor, you can remove the sensible heat out of the floor, roughly 11 BTUs per square foot. But if you need 17 BTUs per square foot, we need to understand how we're going to do that. And it's not really a design flaw, it's more of a physics limit, right? Like, if we can reduce the humidity in the space, it also means that we can drop the temperature of the water without causing condensation on the floor. And it's not difficult to do. The challenge is it's the unintended consequences. If you've never done it before, you definitely don't want to wing a radiant cooling floor. You don't want to wing anything, but there's a lot of radiant heating systems that John Siegenthaler has coined the phrase that they're running but not working properly. You do that with a cooling system, you're going to run into trouble. So the easy way to get around that and the proactive effect is you need to use a dehumidifier. And obviously you want to work with a designer and an engineer just to make sure you're doing the system properly. But the nice part about this is what we're focused on here is lowering the indoor dew point, which is going to allow us to do radiant cooling that will take care of the entire load, because we're going to reduce the humidity in the space, which is going to increase the slab capacity by up to 35%. So as we reduce the humidity, what it means is we can now deliver a much cooler temperature into the slab, and we can go from 11 BTUs per square foot up to 24, 25 BTUs per square foot, because we no longer have that concern of what's going to happen. Is the floor going to sweat? Is it going to be a problem? Now, one of the challenges we have to be aware of is the math that I was talking about very quickly earlier about how many BTUs we can get into that floor. You got to remember that most floor coverings are not going to be just plain tile, right? You get into a situation where you've got a carpet that adds an R value. What was 11 BTUs per square foot could in fact become 15 BTUs per square foot. So we have to be really, really conscious that our supply temperature may have to adjust 10 degrees just to make up for the fact that there's a carpet on the floor. So we need to understand a lot of things with radiant cooling. What is the actual humidity in the space? How are we going to control that latent cooling? How many BTUs do we need? And what kind of floor finishings are going to be in that space? If we design a system around tile and it ends up not being tile, it's going to be a problem. So as we look at what happens, certainly decoupling the sensible and latent cooling loads is really, really important. You can do that through a humidifier. It comes into the open window scenario that I've already walked through. So the whole scenario is that, yes, you've maintained the space. You have not put in the dehumidifier we just talked about, but the window opens up and now you've got this challenge. Well, let's take it a step further. Let's say we do, in fact, put in a humidifier. So I, in particular, picked an Oasis 105 that's designed to remove a lot of moisture out of that space. It's a high performance unit. Well, even with that humidifier running, if somebody opens every window in the home, this is literally my scenario. It was 30 degrees Celsius outside. The relative humidity got up to 76%. And at that point, it's just a massive flood of outdoor humid air coming into the space. And the humidifier just simply cannot keep up with that scenario. So in that particular case, we got to make sure that we have some sort of fallback plan. And the fallback plan is you need to be monitoring temperature and relative humidity and having a dew point controller. So earlier where I talked about the Sky 35 control that I use in my house, it's great for heating, cooling domestic hot water, but it's not going to take care of humidity. It's not going to be able to tell you what is the relative humidity in the space. There, what you need is you need a separate dew point controller. So this is the reactive. This is, okay, we put in an Aprilaire or a Honeywell dehumidifier. We're going to reduce the humidity in the space. We're going to set the water temperature to the floor at 63 or 66 degrees. We'll get 17 BTUs per square foot. But again, what happens if somebody opens all the windows on the main floor? This is the reactive mandatory response, which is a dew point controller. So what's going to happen is it's just a simple relay contact that if the dew point goes too high, it's going to disable the cooling. You would much rather get a call from a consumer to say, hey, my air conditioning isn't working. You go, yeah. Have you got all the windows open? It's 30 degrees out and it's really humid. Oh, yes, I do. It becomes an education point. The alternative is they call you and say, why is my carpet wet? And you go, well, we did put in a dehumidifier, but we didn't put a dew point controller in, so we may or may not have moisture forming on the slab. Give it a couple of days, it'll dry out. Nobody wants to have that conversation. So it is a two-pronged approach, right? So sort of design takeaways as we talk about the challenge in radiant cooling is it's not a radiant problem, right? This whole sensible latent cooling loads, it is a common problem that's showing up in Ontario where the latent and sensible cooling loads are just getting a little bit out of whack. The easiest way to deliver comfort into that space is utilize something that can actually control the humidity within the space, which is going to make it more comfortable, which is reduce the humidity in the summer point. The other thing we got to make sure we do, which we've talked about a lot, is we got to control the dew point, not just the temperature. We got to make sure that we're not just going, okay, I'm going to cool this space because I'm just put the coldest water possible into the floor. That's going to be a problem. We also have to be careful that if we're designing a system around tile, it's got a low resistance finish. If somebody goes in and puts thick carpet in, that's going to have a big, big impact where, yes, if we've done the right water temperature where it's not going to be a problem and we've got a humidity strategy control and a dew point control, it's not going to show up anywhere other than somebody's going to call you and say, I don't know what's going on. My air conditioning's been running all day. It's just not comfortable. And the answer is somebody went in after a designer that you didn't know about and said, we're going to put this really nice Berber carpet that's 2 inches thick. That's your problem. It adds a thermal lag and it can be a problem. So it's really important as we look at radiant cooling that we understand, unlike radiant heating, there's a lot of unintended consequences of assuming colder is better. We cannot put 45-degree water into that slab. In Ontario, with the humidity levels that we have at the temperatures we have, we're going to be well below the dew point. It's going to show up in a problem. Now, the cool thing is, if we do it right, so if we design a system where we can do it properly, it can show up in some really cool side effects. The key side effects is that if you look at what it is to heat a home using water temperatures we do currently for heating, so we're maintaining a slab at 85 degrees. With an air-to-water heat pump, we can maintain a COP in excess of 3. And that's the beauty of an air-to-water heat pump, is we're choosing our emitter. Now, if I put an air-to-water heat pump in and I use a large coil that needs 140-degree water, well, you're not going to have a COP of 3. Like we have the option to choose the emitters. Obviously, a centralized coil at 140 degrees is way less money than doing a radiant floor heating system. But it comes down to, do you want to pay more upfront or do you want to pay less every month? And when you look at the cost of homeownership, it is really interesting if you look at not just the mortgage, but the cost to own the home. And this is something a builder taught me. Builders like hearing from contractors and designers who say, here's your option. Option A is $10,000 to install the mechanical system. And it could be an air to water. I'm just making math up here. Option B is $15,000, but option A, your utility costs every month are $800. Option B, your utility costs are $400. So as a homeowner, the home builder knows this system is going to be easier for them to buy, an easier home for them to afford and live in, and you don't want to dismiss that. Now, when you start looking at a cooling standpoint, if we're doing radiant cooling using 66-degree water because we're controlling the humidity, removing that extra latent load, well, you look at the overall efficiency of the air-to-water heat pump, it is far superior to other systems because we're not having to drive the water down to 45 degrees Fahrenheit, which makes a big, big difference. So that's a really quick, going very fast to make sure we don't run out of time. Like, this is how you can do heating. This is how you can do cooling. We can dive deeper in a separate conversation, but I want to take it beyond that and go, okay, do we always have to do heating and cooling with the slab? And if we don't do with the slab, can we also get a really high COP? So spoiler, yes, we can. And the way that we do that is we look at modern hydronics. So what you're seeing here is 4 different homes. All of them are using hydronic heating. All of them are using hydronic cooling, and they are not using the slab. What's beautiful about this is if you're a homeowner or a builder, you still have no bulkheads. You don't have unsightly sight lines, and it's a very, very cost-effective way to heat and cool. I'm going to use my mouse and hopefully you can see it. One of the emitters is right here behind this grill. This is a wooden grill that's over a heating and cooling convector. The other one is here. So this one is right in front of a wall of glass. You can imagine that what normally would be the least comfortable space is very comfortable. Here's another shot of the same thing. And then over here is another shot of the same thing. So the way they're doing this is they're using low temperature emitters, and these emitters use 95-degree water. So just as a reminder, 95-degree water at minus 20 degrees Celsius, we have a COP of 3.1. Had it have been an air handler, I would have been probably a COP of 2 or a COP of 1.8. So we've gone a different route to try to increase the efficiency. The obvious question that comes from people is, well, how many BTUs can I get doing this? Well, the reality is you can get up to 7,200 BTUs utilizing this unit. More importantly, you can get as little as 1,100 BTUs out of the unit. And this is a photo of a typical convector on the right-hand side. It's designed to be recessed into the wall, recessed into the ceiling. It's very, very compact. All you need to do is run 1/2-inch PEX to it and a 2-wire low voltage connection. These units use DC power. So from a power standpoint, uses basically no power, right? It's a very, very low power device. The key thing to remember here is the challenge that builders face in construction is that loads are getting smaller and smaller, and they're struggling to try to figure out, okay, we need a heat pump, but there's times where the total load we need is like 2,000 or 3,000 BTUs. Well, you look at this unit and realize this is a unit that can do exactly that. It adds other advantages for builders: the no bulkheads, the no taping, the no drywalling, the no painting, There's fire code regulations that help them here. There's zoning from an operative carbon standpoint. There is so many good things in what are on this slide for a builder that have nothing to do with a contractor or an installer. But the key thing is this is a way to heat the home using 95-degree water and getting upwards of 7,100 BTUs per room if you needed that in a very compact and concealed footprint. Now, from a cooling standpoint, in this particular case, I'm using 45-degree water, but the reality is we could use 50, we could use 60, and these same units in cooling can give you anywhere from 1,300 BTUs all the way up to 8,100 BTUs. And the beauty of the system is it's concealed and you don't see it. So if you're looking at what is the advantage to an air-to-water hydronic system, right off the bat, it's smaller and simpler, right? We're not running ductwork. We don't have bulkheads. We don't have the taping and all the drywall and painting. And to be clear, the taping and drywall didn't come from me. It's builders going, Mike, you're missing the plot. It's great it's small. It's great we don't see it. Do you have any idea how much labor you're saving us and how much you're increasing our productivity that we don't need to do those things? Like, okay, I've learned something. The other thing to keep in mind is when you have no ducts, you don't have that air leakage. You're putting these units into the space. All of the air for that space is going into that space. If you happen to be allergic to cats like Mike is, I made the joke earlier, allergic to cats, I have too. The beauty of this system is it allows us to not mix air between rooms. So you can have rooms where the air is kept in that room. The other thing that's really cool about it is it's very quiet, right? So we're delivering comfort without the noise. It gives the zoning options. There is so many advantages to air-to-water heat pumps, and the beauty of it is the simplicity. If you can hook up a half-inch PEX connection, and if you can wire a low-voltage 2-wire connection, you can deliver heating and cooling into the space in a very effective way. So the other topic that I want to touch on, now that we showed, okay, how would we do heating with the slab, cooling with the slab, how would we do heating and cooling beyond the slab, still hold on to the COP of 3, is the last component of the buffer tank. And this is the big question of 2 buffer tank or not 2 buffer tank. And depending on what the application is, there's a yes, you need a buffer tank, or no, you don't. So some of the key things to keep in mind as we talk about buffer tanks is that heat pumps are not boilers, right? Like that is a really, really important thing to recognize. And what that means predominantly is a boiler can lift the water of a system 30 degrees, no problem. An air-to-water heat pump can't. So we need to make sure we decouple the outdoor unit, the air-to-water unit, from the inside system. Because typically on the inside system, we could be running at a 20 or 10 degree delta T, and we want to make sure we don't have a load mismatch there. The other thing that's really important is we want to make sure we don't short cycle the heat pump. Typically what comes into play is people will say, well, I have an inverter, it's going to modulate, I don't need a buffer tank. I have firsthand experience on how that can be a big problem for you. We're going to talk a little bit about that. The other thing is that the buffer tank can improve efficiency and equipment longevity. We don't want the heat pump banging on and off all the time. It's not good for the system. Technically, a buffer tank could also provide for some thermal storage, some thermal inertia within the system, especially if you have different loads. You may, in fact, have one room that only needs 4,000 or 5,000 BTUs. The buffer tank makes sure that your 5-ton heat pump that would be heating the whole home at design and using all 5 tons has a place to put that extra energy so the heat pump runs for a minimum of 10 minutes so that we're not just banging on all the time. And the key thing is when we utilize the buffer tank and we don't allow the system constantly cycling on and off, it's going to extend the life of the hydronic heat pump by many, many years. We do not want to have it banging on and off. It can be very problematic for the unit. Now, as far as types of buffer tanks, I've grabbed 3. There's water-based buffer tanks. There's obviously phase change thermal storage buffer tanks. Anybody who knows anything about me, I like phase change. Obviously, when you're using phase change, it's not a true buffer tank. It acts as a battery, so there's some caveats on flow there. And then the other thing that's really, really cool that I particularly like on these systems is combination indirects. So Heat Flow makes a really good one. I believe it's called the One. Turbomax, which is a Quebec-based company, Thermo 2000 makes a really good one as well. So these are really creative ways that we can use buffer tanks as part of our systems. Now, when we look at the buffer tank and the factors we need to consider when sizing it, I touched on some of them. One is the minimum heat pump run time. There's a lot of studies out there that show the heat pump should run 10 to 15 minutes. The easy example is just imagine if every single time you were going 20 feet in your car, if you were turning your engine on and off, not very good for it. So sort of think of the buffer tank as the cruise control for your system. It limits those starts and stops to keep the system very, very efficient maximizing the COP. And more importantly, it is your built-in anti-short cycling device. So as we talk about buffer tanks, it's important to know there's typically two different types of heat pumps. You have fixed speed heat pumps like geothermal heat pumps, for example. So in those cases, we want to make sure we have a larger buffer tank to accommodate the fact that the unit is 2-speed. There are also variable speed geothermal heat pumps. And then you have a true variable speed heat pump like the HPX5 in my house. So people look at a variable speed heat pump and go, because it's variable speed, I don't need a buffer tank. I like to then ask, okay, was it designed for what temperature? Was it designed for worst case design day? In that case, what happens when it's November? Your heat pump still needs to run. It's at much lower capacity. What does that mean to your heat pump? Is it banging on and off? I also like to ask, what's your defrost strategy? When the unit goes into defrost, is your plan to pull all the heat out of the house? Or do you have a buffer tank there to accommodate that? So it's important that we understand that the buffer tank serves a lot of different purposes. Your buffer tank could also be tied in series with a heat exchanger for domestic, and that buffer tank will make sure that if we're putting out 140-degree water for domestic hot water, then we're not shocking the slab. It gives it a place to go. So the other thing to certainly keep in mind is that we want to be very, very careful about high temperature cycling. If we have a unit that's running for domestic hot water applications, so you take an HPX5, for example, that can get up to 140 degrees, we don't want to be driving it up to 140 degrees, not having anywhere for that energy to go, and then shutting it off, driving it up, shutting it off. There's actually a really good ASHRAE study that shows this is a really good way to kill a compressor. As somebody who's dealt with hydronic heat pumps for over 20 years, I don't need ASHRAE's research to tell me this is a really, really good way to kill a compressor. So we want to make sure that we are installing the heat pump so we have good defrost control. We're making sure the heat pump runs for at least 10 to 15 minutes, and it allows us to keep decoupling the equipment from the indoor loads. Specifically, an air-to-water heat pump would run on a 5 to 8 degree delta T. Your radiant floor system might be running on 10 degree, 20 degree. We want to make sure those two are separated. From a piping standpoint, we have a few configurations on piping of buffer tanks. You have a 2-pipe buffer tank and you have a 4-pipe buffer tank. So we want to be very conscious of what these systems are. I don't really have any preference on a buffer tank without knowing exactly what the system is. The only thing that I would say to you, and you guys will get the Collecti manual for this, which is a really good manual to read. That's where this photo is from, is just make sure that you're not dumping hot water into the top of the tank. That is a really good way to make sure your tank is not stratified. Whereas this strategy here, which would be familiar with anybody who's done a FluxCon buffer tank, for example, it's making sure the hottest water is at the top and the coolest water is the bottom. The nice part about this particular configuration of a buffer tank is if you look at it, it looks an awful lot like a hydraulic separator. It's a really, really good way to decouple the loads, and it's easy to pipe into a system. But whether it's a 2-pipe, a 4-pipe, or a 3-pipe configuration, the buffer tank has a lot of importance. And the key takeaway from this slide is making sure you understand how to pipe it so you don't de-stratify the kit.
Here, Michael.
The actual tank itself.
I just wanted to pop in just because we had a question in the comment section from Blair. They said, I've heard comfort issues with slab cooling at low temperatures. What have your experiences been?
Yeah, so I have an air-to-water heat pump in my house, and I use Yaga low-temperature emitters because the temperatures and humidities in my house that leaks like a cheese grater would be the technical term for it. I get more comfort from using Yaga units. But the reality is, if you have somebody complaining about comfort in the space, it very likely is a control issue. And so specifically what I would be saying with that is that they probably have a water temperature that's not low enough to actually remove the sensible energy. And likely my guess would be that they're trying to keep it above a dew point, but having a strategy for controlling sensible and latent cooling would be critical to how you control the cooling in that space and making sure it's comfortable. Like I can reduce the temperature in my own home, like I can reduce the air temperature, but if the humidity remains elevated, I'm still going to be incredibly uncomfortable. So it's important that we look at sensible latent cooling and dehumidification to control that space.
And sorry, I see there was one more question as well too from Chris. They asked, can these low emitters do latent cooling?
Yeah, so it doesn't change the fact that if you can get the cooling temperature low enough that you can take care of sensible and latent cooling, but you have to understand what is the conditions of your design. Where are you building this house? What is the actual design cooling design day temperatures going to look like? Me personally, I am a big advocate for making sure that we separate sensible and latent cooling, because if I can control the humidity in the home, it makes a big difference from comfort that goes beyond the cooling. One of the things that, we sort of learned, or at least I learned, is we look at this one temperature on the wall, and I'm referring to the thermostat. We go, oh, well, that one number on the wall tells me whether I'm comfortable or not. Well, the reality is that that single number that tells us air temperature is not a good qualifier or indicator of comfort. There's a lot of other things that come into play for comfort. I don't want to get on a tangent here because there's a whole 1 hour discussion we could get into about that. But if you can control other things in that space, like, for example, reducing the humidity in the space and not even look at cooling at all, it can make a huge difference. So in my home, I've got different temperature zones unintentionally. And in the summertime, the way I control those temperature zones is through dehumidification. I want to make sure that I am controlling the humidity in the space as well as the cooling in the space. Hopefully that's addressed it. Obviously, any questions you want to dig more into, we can talk at the end of this. I've got 10 minutes, so I'm skipping a few slides so you guys can get the rest of my presentation. From the standpoint of piping buffer tanks, this is, again, just some typical piping configurations. The one on the far right-hand side is an absolute no-no. You have to be careful dumping into the top of the tank. There are caveats. Some tanks, when you feed into the top, will have a dip tube with a diffuser on the bottom. There's different ways to get around it. But the key thing is we want to make sure we have a stratified tank. So the point of that is that if we do, in fact, need 120-degree water to heat the space, and we mix the tank to 110 degrees, this whole tank needs to get to 120 degrees before we can heat the space. So it's no longer a buffer tank. Your buffer tank is now part of that load and can slow down the inertia of the heating. This particular setup I'm a big fan of. It's a two-pipe configuration. With a two-pipe configuration, what you do is the piping where you feed into the unit, as you get right close to the tank, you're going to upsize that piping. And what ends up happening is it ends up being a point where the velocity of flow drops down. So you can actually be heating the space and charging the buffer tank at the same time. And whatever temperature is leaving your air-to-water heat pump is actually going direct to load as well. So it's a really, really slick way to do the configuration. The last thing on buffer tanks that I want to point out, and this does come into play, is people say, hey, why can't I just use my radiant floor as my buffer tank? Well, the reality is you can, but how much tubing do you have? You need to understand that when you look at half-inch tubing per 100 feet, you've only got like less than 1 gallon a minute of storage within that space. And if you look at how much storage you actually need, well, depending on whether you're at design or not at design, it can make a huge impact. So as far as the formula for how we size the buffer tank around that air-to-water heat pump, it's important that we understand that the volume of that buffer tank is dictated by what is our desired runtime and how much are we going to allow that unit to swing. So what are the BTUs that are going into it? What is that constant load? And what is the minimum heating capacity of that heat pump? So this is a very universal formula that you would use for sizing buffer tanks, whether it's an air-to-water, water-to-water. It doesn't matter if it's a gas boiler, it's all the same. But this is the really big one to keep in mind when it comes to buffer tanks, is the buffer tank at design you may not need, right? If it's in the middle of February, my 5-ton heat pump probably doesn't need the buffer tank. And that's where this particular piping setup is slick. It's a configuration, standard 2-pipe configuration, where that when the heat pump is running, all of the heat that needs to go to the load is going to the load. Any of the heat not needed by the load is going into the tank. So I'm a huge fan of this setup. Also a fan of this setup. It's also equally good. But where it really shines is when you get into those mild weather days where you've got a 5-ton heat pump, but you don't in fact need the entire load. So let's look at that and understand what that means. So a design day heating load, if you look at modern homes that are being built right now, it can be anywhere from 7 to 10 BTUs per square foot. Like, it's very, very low. And even if you're looking at 14 to 20 BTUs per square foot, what happens during the shoulder season where we only have 20 to 30% of design? And that's where it's really, really important that we pay attention to what's happening. So if we look at heating at design, and if you looked at an HPX3, which is a 3-ton, or an HPX5, I've put 3 scenarios up where I can make a really strong argument that I don't need a buffer tank. I can make this unit run at design, don't need a buffer tank. The challenge becomes that when I start to get into the shoulder days, we need a buffer tank, right? When you look at what does it mean when I only need 3,000 BTUs to heat that space? Well, the inverter drive can't get that low. The inverter drive is still trying to deliver 9,000 BTUs. So I need a buffer tank. We have to make sure that when we look at a buffer tank, we're not looking at a Polaroid picture, right? It's easy to go there in February and go, yep, everything's working great. And then they call you in April and go like, I don't know what's wrong. My unit keeps locking out at high pressure. I can't explain why. And I know why. It's trying to deliver BTUs into the space, but it's trying to do it with a fire truck, right? So you need a garden hose and somebody's pulled up from the fire department and they're literally sandblasting your system with that many BTUs. That's the effect of no buffer tank when it's not at design. Well, what does that mean? Well, what that means is that even if you have an inverter drive, if you don't design your system properly, you can end up in a situation where you have massive, massive cycles per hour. Like you have a situation where a system's coming on and off all the time, and that frequent start-stop will cause issues with that compressor, and that compressor will fail. And that can show up as quickly as 1 year into the heat pump running. And the solution to this is very simple. One, don't run it at 140 degrees if you only need 100-degree water. Understand your application. And two, don't just read something on the internet or come to a 1-hour training session and go, oh, Mike said I don't need a buffer tank. The buffer tank is dictated by the design. What is the load on the degree day? What is the load on non-degree day? What does the house look like? Is it an air handler? Is it radiant floor? Is it a low temperature convector like I showed you? There's so many options that we need to make sure we're aware of, but just understand with an air to water heat pump, it's easy in my opinion, but if you miss a step, you can end up with problems that can be quite expensive that you don't want to deal with. Quick look at a schematic as to what a system would typically look like as we wrap up here. Again, this is a really nice schematic provided by Cleffy. The plumbing and HVAC team will provide you with the PDF manuals. They're very detailed. They're fantastic manuals. I like them. What this is showing is it's showing an air-to-water heat pump. It's showing an Argosys buffer tank. So this is the tank that has 4 ports. There is a variety of different ways to pipe it. The way that this is being shown to pipe is they're coming up over the unit. They've put ample sized fat piping. So what they've done here with the piping is as they come to the top of the unit, they've sized that piping so the flow velocity drops below 2 feet per second. And what it means is that in a heating situation, we're getting all of the energy going out to the emitters, which is really, really cool, right? So if we don't have any emitters running, it's charging the buffer tank. If the emitters are running, whatever the water temperature we need is going directly to the load. So it's a very, very cool, well, hot way, I guess would be the way to put it, that you could design the system and make the system work. This last method, and this is a method that we use using the HPX5 and the Sky 35 controller I showed you earlier, is the Sky 35 controller has the ability to control the heat pump. It'll control the indirect, both heating and cooling. And in this particular case, it's a diverter valve. So the idea being that is if we ever have a cooling call, we're going to actually divert, not charge the buffer tank, and deliver the coldest water possible into the air handler. So where we were talking about comfort, if we're not going into a radiant slab where it's 66 degrees, we're actually going out to the air handler. We want to have water temperature as cold as possible, getting it down to 47, 46 degrees. Well, if we feed it into the tank, there's potential for mixing. So the diverting 3-way valve allows us to deliver the chilled water directly to the air handlers because we're not typically going to have microzones. Like if you look at my in-floor examples, there's zone valves feeding them. So you could have situations where you do, in fact, need a buffer tank. But typically with air handlers, you've got enough capacity that you're never going to drop below the minimum of the inverter drive. So I have exactly 3 minutes left, and I'm getting very, very close. And this is the last thing I want to touch on. And that is where air-to-waters are really, really cool is their thermal storage capabilities. So if you look at a radiant floor heating system right now, if you put a boiler on a radiant floor heating system, it doesn't matter when you use that gas. The really cool thing is, if you're the IESO and you're looking at, hey, what technology do we want? You 100% want an air-to-water heat pump or a water-to-water heat pump. And there's a really easy reason why. This is a study that was put out by Navius Research. And what it shows is that if we were to utilize thermal energy storage, we could trim almost 20,000 megawatt hours off peak. That ends up being a peak load reduction of 25%. And then it leads to the question, well, how do we do it? The answer is easy. For every gas boiler that comes out and gets replaced by an air-to-water heat pump, that's a thermal battery that can hold tens of thousands of BTUs directly in that slab. And we've seen this. Anybody who's been around a hydronic heating system knows this, that if we install a hydronic heating system and if we don't use floor sensors, the number one complaint we get is it's so hot in here, it's so miserable. And then you're telling that end user, turn the heat off, wait a few hours, it'll cool down. Well, the nice part about an air to water heat pump in that scenario is that we can charge that slab off peak. We don't need to overheat the space, keep it comfortable, hold that heat, dodge the peak, and utilities would really like air to water heat pumps. So I finished, Francesco, with a minute and a half left to go. I apologize if I talked really quick. That's what happens when I go twice, but I hope everybody got a little bit of value. Thanks for coming.
No problem. No. Again, we just want to take a second to thank everybody for sticking with us through the technical difficulties. We really, really appreciate it. We love putting on these events, and the main purpose for these events, is to provide good quality technical training to everybody. So we hope that people, leave with a little bit more information than when they came into the event. And just for reference, everybody, like we said, we will be posting all of the sessions on our YouTube page and our Training Trades website. So you always have a recording of the video to go back and watch the presentation. We also will be handing out those handouts that Michael was referencing throughout his presentation. We will send an email through the Excel software, kind of just highlighting those documents. And again, each of these presentations that were featured today will be turned into an article that will be featured in our next issue of the magazine. It will be in our own, hydronics heat pump supplement. So please look out for that as well, too. And our next technical training day will be, I believe, in February, and it'll be on water treatment. So stay tuned for information regarding that. Again, we want to thank Michael so much for taking the time to present, not just once, but twice. And I think he did better the second time. I think it was a little bit better. So we appreciate everybody sticking with us, and we would look forward to seeing you guys at our next event. Thank you, guys.
Yeah, this QR code is me. You guys want to hit me up on LinkedIn, any questions, anything we can do to help, reach out. I appreciate everybody making the time.
Thank you, guys.